So last time we were talking about single particle dynamics, so Newtonian mechanics. We looked at 1D examples, one main dimension, and then a couple of 2D examples, the projectile motion, pendulum. Today we'll talk about kinetic energy, linear momentum, and angular momentum. And it's going to be quite a bit of theory, but we will do an example or two. So that's where we are, and that is where we're going. So first, let's talk about energy. Actually, both energies. It's not just kinetic energy. This is energy of a single particle, and I guess this is section 2.3.3. So often you'll be just told this is what kinetic energy is. Kinetic energy is 1/2 mass velocity squared. So let's first just look in 1D, and most of this stuff carries over to 3 dimensions. So many books will just define it. Kinetic energy, 1/2 mass times the velocity squared. But you might wonder, where's that coming from? It feels kind of unmotivated. Why does this depend on v squared? Where's that 1/2 come from? So I want to give you a couple of ways to see this. And as an added benefit, we'll be able to understand why total energy is conserved, so kinetic plus potential, without really doing any further calculations. I'm going to draw a picture for you. So we're just looking at a one-dimensional world. And let's say we start off over here with an initial velocity at time 0, that's 0, and at some intermediate time, we've got a force. And the force is bringing us up to our final velocity, which we'll just call v. And let's say this happens over a distance d. So there's a calculus way and then a calculus-free way. Let me give you the calculus way. We also need a notion of work. What is work? Work, it's the energy put into a particle due to a force F. Energy, so it has units of energy done to a particle due to a force F. So I want you to think of just a general force right now, and we're going to calculate the work done by the force, which becomes an integral. We'll call this dimension x. The work done by the force is the integral of f dx. So it has units of work of force times distance. This force, we could also write it as 0 to t, and we'll write f, could be a function of time. And here we'll write v t times dt. Why is that? Because v is dx by dt. So we could just substitute in, for dx, we'll put in v times dt. So that's where this part comes from. And now we could substitute in Newton's law. We'll use, for Newton's law, F equals m times acceleration, but that's the same as dv by dt. So the integral of this, the initial time to the final time, is m dv dt v dt. I want you to notice, what is this? You could also write this as it's the derivative with respect to time of 1/2 v squared. Right? If you take the derivative with respect to time of 1/2 v squared, you'll get v times dv dt. So we'll just go ahead and put it in there. So the f dx, that's the work done by the force to get the particle from speed 0 up to its current speed v, is equal to, we could pull out the m, 0 to t, d by dt, 1/2 v squared dt. And hopefully you'll look at this part and go, okay. So by the fundamental theorem of calculus, this integral is just 1/2 v squared, the current times velocity. So that means we get m. So we'll call this the kinetic energy. The kinetic energy is, here's how we'll put it. Kinetic energy is the work done on the particle by force to get it from speed 0 to the current speed v. So hopefully that gives you at least a better appreciation of where kinetic energy comes from. There's a calculus-free explanation. We think of accelerating our mass with a constant force from speed 0 up to speed v. And I'll use that diagram. Maybe I'll draw it again. So our initial speed is 0. We're going to take it up to speed v. And throughout, there's a force. And it doesn't really matter what the force is. So here's a calculus-free explanation. So if we do F times the distance d, right? So we're speeding this up from 0 to v. So we've got force times distance, which is m times the acceleration times distance. So we just plugged in F equals ma. And this is going to be, we'll just say, say this is accelerating at a constant acceleration. So for the acceleration, we could just write v over t. And then what is the distance traveled is the average times t. The t's cancel out. This v is the average speed traveled. So the average speed isn't 0 and it's not v, it's actually v over 2. So the average speed is v over 2. So now we still get 1/2 mv squared. So you might think about that, but it does, at least help us. Where does this 1/2 come from? It comes from in some sense, the average speed to go from 0 to the current speed. And it's v squared because the force and the distance traveled will both depend on v. I'm doing this just to give you some intuitive idea of why you have 1/2 mv squared. And this extends to multiple dimensions. So in 3D, right, we would say the velocity is the magnitude of the velocity, which is the magnitude of the inertial derivative of the position. So if we want, let's draw a little sketch of an inertial frame with an origin. And here is our current location of the particle. It's probably traveling through some path. It's got a speed, a velocity, r dot. And by this, I mean derivative with respect to time and also with respect to that inertial frame. And there's a force acting. So in 3D, we could write the kinetic energy. It is still 1/2 mv squared. But if we want to write it in terms of the vector of the velocity, this is r dot dotted with r dot. You can write it that way. How does this relate to the total energy? Well, let's go back to the 1D world. So 1D again. We started out writing this as the work done on the particle. And now I'll write F as a function of the position x is equal to, we know, going from one speed to another speed. So say going from v1 to another speed, v2, with a force acting the whole time. This will be 1/2 mv2 squared minus 1/2 mv1 squared. This force, often the forces that we'll deal with will be conservative, meaning this force can be written as the negative derivative with respect to a potential energy. I'm going to call that capital V. All right, which means, plug that in here. We have negative dv dx dx. And this, again, by the fundamental theorem of calculus, is just the potential energy. We've got a minus in front of x2 minus potential energy at x1. So let's carry through that minus sign. What do we get? Potential energy at x1 minus potential energy at x2. So the work done can be written in terms of kinetic energy, and it could also be written in terms of potential energy. Right, that's P. So we've got 1/2 mv2 squared minus 1/2 mv1 squared equals vx1 minus vx2. And we could write this as the 1/2 mv1 squared plus potential energy equals 1/2 mv2 squared plus potential energy. We would say this is the energy at position in time 1, and this would be the total energy at position in time 2. E equals T plus V is what we'll call the total energy. And this works in 3D as well. In 3D, we have F equals the negative gradient of a potential energy that depends on the position. Say for conservative forces, often this is what's meant as a definition of a conservative force. It's the negative gradient of a potential energy. So if you work through the integral for work, you will get the same thing, that it's the change in kinetic energy. So between two different, from say final time minus initial time, the change in kinetic energy is equal to negative of the change in the potential energy, right? If you go through the integral of work, this would be F dotted with dr. So it's just the 3D version of F dx from the position at the initial time to position at the final time. You substitute in, and you'll get that this is negative dv between those two times. So this is negative v at the final position minus v at the initial position. So this is the change in potential energy. So the change in kinetic energy is negative of the change in potential energy, or we could rewrite it in terms of total energy. So kinetic energy at the final time plus potential energy, the final time, is equal to kinetic plus potential energy at the initial time. Call that capital E, total energy, capital E, total energy. So total energy is conserved as the particle moves through a conservative force field. So for example, gravity. There's other situations too, but gravity would be the main one that we care about. We're not going to use this yet, but part of what you're going to be doing over the next couple of weeks is, where appropriate, using conservation of energy to solve problems, rather than just writing Newton's laws, using conservation of energy, along with conservation of either linear or angular momentum. So let's talk about momentum. Momentum of a single particle. We've got linear and angular momentum. Linear, we'll use the symbol little p vector, and the linear, a better name might be translational momentum, but we're stuck with the names we have. So this is related to translational motion. That's the usual motion that you think of, going from here to here. It's translating. Angular momentum, we'll use capital H vector, and this is related to rotational motion. So eventually it'll be related to the rotational motion of a rigid body. And we'll talk about how is it related to a single particle. What do we mean by rotational motion of a single particle? And this is a high-level view. We'll look at details of this. The equations of motion can be written in terms of how these things that we call linear and angular momentum, how these vectors change. So P dot, right, which means the derivative with respect to time and an inertial frame, equals the total force. And for the rotational motion, H dot, by which we mean derivative with respect to time and with respect to an inertial frame, and that'll be equal to something we haven't yet talked about, but the moment, total moment. So we're going to unpack these, go into more detail about where they come from. We might call these the linear and angular momentum rate equations. So the equations of motion are the linear and angular momentum rate equations, right? Because it's giving how do these vector quantities change with time. So let's unpack these. The first one, linear momentum. Let me draw a picture. Just sketching out, here's a inertial frame. And we've got a point mass, a particle. Here's the vector to the particle. We'll just write that as r, the position. And this will have, pardon me, a velocity, which say maybe you could say that's from kinematics. This is the inertial velocity of the particle. Linear momentum, it's defined as mass times the inertial velocity. And if we take its inertial derivative, so p dot, this is m dot r dot plus mr double dot. Because we're talking about a particle, it can't change mass. So you might be wondering, well, how would I do the rocket equation? If you have a system that has a time-varying mass, you need to treat it as a multi-particle system. So we're left with p dot equals mr double dot. And mr double dot is the usual way that we've seen Newton's laws. But you could also write it as p dot equals f. Where it's understood, this is for a single particle of constant mass. So if you've seen the rocket equation or you know about it, they always sneak in some kind of m dot term, but they are assuming it's a multi-particle system. That's the only way to get that, because particles need to, for you to go one way, particles need to be exiting the other way. So when I write this, this is just for single particle of constant mass. All right, so that if in this diagram over here, we've got, let's just say instantaneously, our particle is moving with a speed or vector, r dot, and we've got the p vector is parallel to that. It's in the same direction. And how does p change with time? Here's p dot. P dot changes, and it changes exactly to equal what the total force is. F is the total force on the particle. So you could, it's just a way of trying to visualize what this vector equation means. And it's probably worth stating at this point what the special case is. The special case of this would be if there's no force. So if the force is the zero vector, then p dot equals 0, which means that p equals constant. It's a constant vector. So p at any time t is equal to whatever p was at an initial time. So that special case, if the total force is 0, right, there could be forces on this, but they counterbalance. So if you've got that, this is another way of stating conservation of linear momentum. All right, so that's linear momentum. Let's talk about angular momentum. You watch me draw another picture. There's a particle, m, and we'll deal with the momentum. That's the linear momentum. And then there's also force. So angular momentum is trickier because it's always with respect to some point. Maybe I'll even say that. It's trickier because it depends on a reference point. So the first reference point that you would pick would, in this case, be if R is the position of the mass with respect to the origin, or another way that we might write this, from the origin to M, we've picked what our reference point is. It's sort of hidden in here that our reference point is the inertial origin O. So let's assume that O is inertially fixed, the origin of this end frame. Then we write the angular momentum, and I'll just put this in words because this is where it can get tricky. The angular momentum, you always have to specify what the reference point is. So angular momentum with respect to O, or sometimes we might say or write angular momentum about O, and this will be a vector, and we usually write the reference point. So capital H sub O, and it's going to be R of M with respect to O cross P of M with respect to O. And I'm just putting these additional subscripts in there just to make life easier. R is RMO, we've already said that. P is PMO, which means it's the mass times the rate of change of that position vector. So if we put that in there, and then you could also, if you want, say, all right, this is R cross M R dot. Just substituting in the definition of linear momentum. So that's the angular momentum of this particle P, or mass M, with respect to the inertial origin O. And now we're going to take its derivative, kind of like we did up here. We take the derivative of this linear momentum, and it equals mr double dot, which we know from Newton's second law is the total force. So now we'll take the inertial derivative of the angular momentum, which will then give us the angular momentum rate equation. So take the inertial derivative. Another way to write that, the compact way, is h dot, but just to remind ourselves, it's derivative of this vector h with respect to the end frame. And maybe over here I'll sketch what is f, or what is h. So r cross p, I don't know, it's something. It's some vector in three-dimensional space. This derivative, just plug in what we have. Inertial derivative, meaning derivative with respect to the end frame, of r cross p. And now we use a property of the derivative of cross products. So this is, it's the product rule, but for the cross product of a vector. So it's the derivative of the first vector cross the second one, plus the first vector cross the derivative of the second vector. All right, so what is this? This would be, let me use that color. This is r dot. Let's make it more clear that that is r dot. And what is p? This is m times r dot. So we've got, if we pull out the m, we've got m of a vector cross itself. Any vector cross itself is just 0. What about over here? The second term, this is p dot. So we've got r cross p dot. But what have we said p dot is? We've said that p dot, right, this is just from Newton's law, this is equal to the total force F. So we summarize this. The inertial derivative of the angular momentum is r cross F. And because we're going to be using this quite a bit, we're going to define this right-hand side as something that we'll call the moment on the point on the mass M. So maybe up here, I need to, I'm running out of colors. Here's one. M. So let's define the moment on particle M due to force F. So that's M is R cross F. So another way that you could write this would be the time rate of change with respect to the inertial frame of the angular momentum vector equals the moment. So now we've got an angular rate for, or we've got a rate of change equation for the angular momentum and a rate of change equation for the linear momentum. Now, also to be clear, we might add a subscript because this will come up. We mean the moment with respect to the point O, right? This was a moment that's related to that point O because we're looking at the position of the mass with respect to the point O. So maybe everywhere here we'll put O, O, and even add it into here with respect to point O. And I'm writing it this way because eventually we're going to be taking, you could take the moment with respect to some other point. You could even take the moment with respect to a point that's moving, not an inertially fixed point. So let's apply this to an example. So this is going to be a worked example for the pendulum. And hopefully we'll get the same answer we got before when we used Newton's laws. You might wonder, why don't I call this torque? I mean, you could. I'll be using moment. In my way of speaking, I do not distinguish moment or torque, but the book uses moment, and so I'll use moment. They are, as far as I know, physically the same thing, and there's no reason to nitpick. All right, so let's apply this. So we're going to apply the angular momentum equation. We haven't given it a name. Angular momentum rate equation. Some people call it Euler's equation, which is going to be confusing later. There's too many Euler's equations floating around. The angular momentum rate equation, or we might call it the rotational dynamics equation. And I mean this one here. So here's an example, the pendulum. So same setup as last time. So if you remember what that was, we have what's a pendulum? The pendulum is, write it this way. Maybe I'll move the pivot a little bit down. So we've got a mass connected by a massless rigid rod. So it's an idealized situation. Here's our mass. We could define an inertial frame. Here's N1, N2. N1 is horizontal, N2 is pointing up. So it's opposite gravity. We got gravity pointing down. Hopefully we may have enough intuition about the pendulum that we know, oh, okay, it's mostly rotational. So it kind of makes sense. Let's use rotational equation, not Newton's law, something rotational. So we'll use theta. It seems like the motion is mostly rotational. So rotational equation, rotational dynamics is appropriate. All right, we'll use this angle theta, and we'll use the polar coordinates like before. This has a length L, so that's the length of the massless rod. I will attach the frame. This is a polar coordinate frame. So ER, E theta, and then E3, which is going to be the same as N3. the direction coming out of the screen is the same. And why is that? ER cross E theta, if I use my right hand, is pointing out. So we've set it up so they have the third direction pointing in the exact same direction, which makes life easy, at least easier. Okay, if we want to describe what's the position of this, I'll use orange, that's R. We'll name the pivot O, and it's inertially fixed, so that's good. So I might just write it as R, but this stands for the position of the mass with respect to the point O, meaning it goes from O to M. What else? We've got forces. So if we were to look at the forces on this, let me do a separate little picture down here, free body diagram. We've got the tension in the rod and then gravity. So we'll call this FL, and we'll call it, it's a vector, FG. Total force on M, F is FL plus FG. All we need to know is that this is FL is parallel to ER. That's all we're going to need to know. If we want to, we could write it the way we did, I think last time, it was like negative N ER. It doesn't really matter if it's plus or minus N. It's not a big deal. It's just some amount in the ER direction. So we've got the total force. I don't even know if you add these two, what does it give? Maybe something in this direction. All right, now we can use that angular momentum rate equation, or the rotational dynamics equation. We want to use this. So we got to figure out what these things are. All right, what is HO? HO is R cross P. So that's R cross M R dot. And we can write out what all of these things are. R is L, right? Remember, this is the vector from O to M. It's L in the ER direction. And what is R dot? Right, that's the inertial derivative of R. So it's L, because that's a constant, so it's not going to take a derivative of that. We've done the derivative of polar coordinates, but I'm just going to do it again just for good practice. What is this? So L times, and now we'll use the transport equation, which would be, because this vector is defined with respect to an E frame, a frame that rotates with respect to our inertial frame, we take the derivative of the ER direction with respect to E plus the angular velocity of the E frame with respect to the N frame cross ER. This is 0 because the ER direction is constant in the E frame. And what is omega of E up here in the left? E with respect to N. The E frame, if you think of the two frames as initially aligned, so ER pointing downward, I use my right hand, I curl my fingers in the direction that theta is increasing, and my thumb is pointing in the E3 or N3 direction. So that means the rate is that angle dot. So theta dot, and then E3. All right, so then in here, if I evaluate this, we've got theta dot E3 cross ER. As much as possible, I avoid doing the cross product using that weird determinant thing. You don't really need to. So what is E3 cross ER? Okay, this is E theta. All right, so this was a lot of work to show that this is L theta dot E theta, which maybe we remembered from before, but there it is. Okay, so our goal is to get what this angular momentum is. So it's R cross mr dot, plug in what we've got here, and we get, we'll get m L squared theta dot ER cross E theta. So now we got to do another cross product, but it's all right. They're all in the same frame, at least in this case. ER cross E theta. This is in the E3 direction. So our angular momentum is ML squared theta dot E3. Cool. Now we could take, and remember E3 is the same as N3. It might help us conceptually if we think of it as, so we don't get confused. It's in an inertial direction. It's in the N3 direction. Why do I want to emphasize that? Because now I need to take the time rate of change of this. This will be the left-hand side of my, this purple highlighted equation up here. So it'll give me the left-hand side, and then I'll get the right-hand side. I'll evaluate what this moment is, and I'll have my equation of motion, the second order ODE for theta. All right, so this is H dot is shorthand for inertial derivative of the H vector. And notice over here, because this is written in terms of n frame components, I don't have to mess with the transport theorem. So that's good. So I could just immediately take derivatives of this stuff in here. ML squared theta dot. This will still be in the N3 direction. The only thing here that can change in time, right? Mass is constant, length is constant, theta can change. So this will give me ML squared. Take the derivative of theta dot, I get theta double dot N3. If I call this equation star up here, so now I've got the left-hand side of star. Now I want the right-hand side. So to get the right-hand side, it means we're evaluating what the moment is. Let's draw a picture, again, of our situation. Here's R, and I've got a couple of forces. I've got FL, and I've got FG. I haven't even said what FG is. Maybe I haven't said what FL is, except that it's parallel to the R direction. So if I evaluate what the moment is about the point O, this will be R. Remember, this is M with respect to O. That's where the O part comes in. Cross the force, total force on that particle. So I could split this up, and I'll drop the subscript MO because we know this is just the one position vector that we're dealing with. R cross, now what was my total force? FL cross FG. All right, so R cross FL plus R cross, this is not a cross, this is a plus, isn't it? No, that is a cross, and this one is a plus. Plus R cross FG. This is 0, since FL is parallel. Even if it's anti-parallel, they're along the same line, parallel to R. This other one is not, though. What is FG? FG is mg and in the negative n2 direction. So we're left with evaluating this. What is this? This is LER cross mg, let's do negative mg n2. Right, because this was the n1 direction, this was n2. If we need to remind ourselves what it was ER, it is this direction, ER. This angle is theta. So MO is negative MGL times this cross product ER cross N2. And now you might go, oh, now I need to write N2 in the E frame. Yeah, I guess you could do that. You don't have to do that though. Remember the other way to write this? If you have a cross product of two vectors, then it's going to be equal to, so do ER cross N2. My thumb is pointing in the N3 direction. But because these aren't from the same frame, we need to take into account sine of the angle between them. So it's sine of the angle between them. What is the angle between them? Let's draw these again. Here's N2. Here's ER. This is theta, which means that this is pi minus theta. Okay, that's the angle between the two. So sine of pi minus theta. And now by a trig identity, sine of pi minus theta is the same as sine of theta. All right then. So the moment is negative MGL sine theta and in the N3 direction. So that is this would be the left-hand side of that rotational dynamics equation, or the angular momentum rate equation. So now we've got both sides. We got this and we got this. Yay. And they're both in the same direction. They're both in N3. So these two vectors only have an N3 component. So HO dot equals MO only has an N3 component. So set them equal. We've got ML squared theta double dot equals negative MGL sine theta. And typically we only want, we want to put this in the form of the rate of change of our thing equals something. So get our highest derivative by itself on one side, which means in this case, we divide both sides by ML squared. So this gives us theta double dot equals, the masses cancel out and we get negative G over L sine theta. So this is the same ordinary differential equation for theta we got using Newton's laws last time. And it, it looks like it took long because I was being careful and trying to show you, but some of these steps would be, after some familiarity, it would be easier. So, okay, good. The universe holds together and two different methods can get the same thing. What if, so here's me with the pendulum, my pen. What if the pivot's moving? Well, if the pivot's moving, then things are different. So what if the pivot for the pendulum was moving? And you maybe like my hand arbitrarily. So one problem that describes this is the pendulum attached to a cart that can move horizontally. So let me sketch that out. If we have that's our sidewall, and then here's the track that their cart is on. So by a cart, I mean something that's moving back and forth. And in this case, it's moving arbitrarily. Maybe we'll call this point, instead of O, we'll call it P. So if the pivot P was moving, and we'll track how it's moving, we'll measure that from the wall as X. And then this is this is a pivot point for the pendulum. So here's our pendulum. So we could still track theta, but now we also have x to deal with. So by arbitrarily moving, I'm thinking maybe x is moving kind of erratically. Let's say it's not negative. It's just kind of moving. So we're going to treat P as an arbitrarily moving reference point. And then how would we do that? Well, let's sketch the situation. We've got, there'll still be, for us to write Newton's laws or take a derivative with respect to an inertial frame, we need an inertial frame. So there's always going to be some inertial frame. And now let's call this point arbitrary reference point. We'll call that P. So we need to track the location of, we'll still call this O, P, and this is the vector from O to P. And we have our particle M. And for whatever reason, we have found it convenient to write the location of the particle M relative to P, or location of particle M with respect to P. It's probably easier just to write what these things are. The book will call this vector sigma. So R is from O to M. RP is from O to P. And sigma is from P to M. So we could write it in terms of R and RP, because often we'll be tracking how does this point P move and how does that affect the dynamics. We can, and this might be, I guess this is getting to the point of angular momentum being trickier because it always has a reference point attached to it. We can define the angular momentum of M with respect to P. So this is the angular momentum vector of M with respect to or relative to P, or about P. There's different ways that people say it and write it, but it's all the same concept. So we'll write HP. So this will be the angular momentum of that point M, but with the reference point P now. This will be the vector describing where M is with respect to P cross M sigma dot, where, as usual, if we write a vector with a dot over it, that means the inertial derivative of that vector sigma. Okay, and then now that we've defined this, we would take its inertial derivative, because at the end of the day, we want to get a rate equation for how HP changes. What we'll get is HP dot equals some moment, but there'll also be a term that's related to how the point P is moving. So let's just take HP dot for now. Take the inertial derivative, HP dot. That means inertial derivative of HP. And now just plug in how we've defined it here. Sigma cross M sigma dot. We're going to have to take that derivative. So like before, we use the product rule for cross products. So we take the inertial derivative of sigma plus, or cross M sigma dot plus sigma cross M inertial derivative of sigma dot. The M is a constant, so I pulled it out. This is just sigma dot. So I've got sigma dot cross some scalar times sigma dot. So that's going to be 0. And this, I'll just call this sigma double dot. So we're left with sigma cross m sigma double dot. But what was sigma? Look up here, right? This is at the top how we define sigma. And we could take two derivatives of that. So sigma double dot equals r double dot minus r sub p double dot. So this is sigma cross m r double dot minus r p. So this is where the motion of p enters. So it's really just the acceleration of p that matters. If we carry this through, we've got sigma cross m r double dot minus sigma cross m r p double dot. This term, this is m r double dot, mass times acceleration. It still obeys Newton's law, so this is equal to the force. And then this other term, it's often just written in reverse order. So to get rid of this minus sign, this just gets written as mrp double dot cross sigma. So now we will, define the moment on m with respect to the point p. So m sub p is sigma cross the total force on the particle. And why am I doing that? Because these two together, this is sigma cross f. So we've got m p, the moment about the reference point p, plus this other term that takes into account how p is moving. And remember what this was? This was hp dot. So we've picked up some term. So this is the moment due to forces. And then this would be, it looks like a moment due to the motion of the point P. And that this disappears if P is moving with no acceleration. So if the acceleration is 0, meaning moving with constant speed and constant velocity, that term would drop out. But in general, it won't be. So it is going to affect, say, how the pendulum moves. So this is probably you learned from Miriam and Craig. This is equation 2.37 in Schaub and Junkins, but it's also equation, they use slashes, 413 in Miriam and Craig. They probably intended to use it just for like 2D things. We'll be using this for 3D things. And if you apply this to the cart pendulum problem, here's what you'll find. Theta double dot, this is the equation of motion for theta. It ends up being negative g over L sine theta. Hey, that makes sense. That looks like the normal pendulum, but then there's this other contribution, x double dot over L, where x double dot has units of acceleration, so just like acceleration due to gravity. And then this is a cosine theta. So this is the contribution due to the moving pivot. So as the cart moves around, you can, and it has to be accelerating. If this was just moving with a straight line, then the dynamics of the pendulum would be, or moving with constant speed, the dynamics would be the same as the normal pendulum. This is why when you accelerate, if you've got something hanging from your rear view mirror, right, only during acceleration do you see that the hang tags kind of move backwards or whatever, you're hanging tree to make the car smell nice. So that's the contribution due to a moving pivot. And then this would be related to a control problem. Can you pick X as a function of time to make the pendulum go from down to up? It's a classic problem in control. I'm not going to ask you to do this. I just want to give you an example of how this would be used. Given the goal of making a pendulum go from down, so that would be theta equals 0, to upright, theta equals pi, how do you pick x as a function of time? And probably you wouldn't just pick an x as a function of time. You'd pick an x that is a function of theta, which would be a feedback control law. But that's a controls problem that we're not going to tackle here. We'll tackle some other controls, but not that one. It just gives you an idea. And ideally, you pick it so that this is stable to disturbances. All right, I'm gonna stop there.